Today's paper is Contrastive Learning for Unpaired Image-to-Image Translation. The work performs an image-to-image translation task based on contrastive learning. Instead of operating on an entire image, the method works on image patches. The proposed model encourages two corresponding positive image patches to map to a similar point in a learned feature space relative to other negative patches in the image. The framework enables one-sided translation tasks with unpaired images while improving quality and reducing training time. In image-to-image translation, the target is to let the output image take the appearance of the target domain while retaining the structure of an input image. This is seen as a disentanglement problem which targets to disentangle content and appearance. Usually, appearance of an image is captured by an adversarial loss, while content is preserved using a cycle consistency loss. However, the authors claim that cycle consistency assumes relationship between two image domains as a bijection, which is often too restrictive. In this paper, a straightforward rate is proposed. The model maintains correspondence in content but not appearance by maximizing the mutual information between corresponding input and output patches. The figure shows the general idea of the proposed method. As shown in the figure, given a specific patch on the output, corresponding input patch colored in light blue is selected as a positive sample, and random patches are sampled to be used as a negative set. With the sampled patches, the model uses multi-layer patchwise contrastive loss that maximizes the mutual information between corresponding input and output patches, and this enables one-sided translation in the unpaired image settings. Now, this figure shows detailed view of the patchwise contrastive loss. Both images x and y hat are encoded into feature space. A query patch comes from the output image y and is compared to the input patch at the same location. Using one positive patch and n negative patches, a n+1 wave classification problem is formed. The encoder of generator G is reused and two-layer MLP network is added to project both the input and output patches to the shared embedding space. Note that the features are gathered in multiple encoder layers to capture features of different sizes. The table shows contrastive unpaired translation, also called as CUT, with other image-to-image translation models. The FID score of CUT model is lower than other models on cityscapes, cat-to-dog, and horse-to-zebra datasets. Also, on cityscapes dataset, the model outperforms other models in semantic segmentation scores. The fast CUT model, a light version of CUT with less training time, also achieves competitive results. Now here, the left figure shows comparison of CUT with other one-sided and two-sided translation models. On horse-to-zebra, cat-to-dog, and cityscapes datasets, CUT model generates successful cases compared to other two-sided methods like CycleGAN, Munit, and DRIT. The last two rows show failure cases of the CUT model. The horse in the source image was not captured, and thus the model applied zebra texture on the background of the image. Also, the cat-to-dog sample in the last row show the false generation of a tongue. And on the right are the additional results of the model. Link to the paper and some useful resources will be provided in the description. That's all for today, and I'll see you next time with a new paper.